Yeah, so where we were earlier was to create the model, the path model, okay? Good. So as I was saying earlier, this is how the data looks like. This is your data correlations and then the indicators, all right? You have the various indicators, and then the mean, max, and all those things. Okay, good. Yeah. So I will plead that everybody mutes their microphone and their videos so the streaming can be quite fast. If you can do that for me, please. Mute your videos and your audios. Yeah. Okay, good. So now we want to create what we call the path model. Okay, we want to create the path model. And we are going to create the path model based on this. You are able to see the whole desktop, right? Good. All right. So the path model, this is how it is. So we're going to create the path model. Now, what you do is that you go and double click the path model here, as I was creating earlier before I went offline. Then you choose okay. You choose the various connectors, okay? You connect from here to here, connect this one to here, connect this way from here to here, and this other one to here. Now, you can click on select and then rename the latent variables, okay? I am under the impression that we all know what latent variables are and what observed variables are. Okay, good. So we're gonna have performance. Okay, so we have performance, we have effort expectancy, we have social network or social influence, you have facilitating condition, you have behavioral intention, and then actual use behavior. All right, all those are the constructs for the tout model. Good. So you rename all this in line with what you have over there, okay? Now, after you are done with that, then you go and you pick what we call the indicator variables, okay? You select them. So for instance, performance is P, PE1, PE2, PE3, all right? If you are following my mouse over here, to your left, you see the indicator. Please keep your eyes on the mouse. Then you select all of them, you drag and you drop. It changes from red to blue. Okay. So we have PE1, PE2, PE3, PE4. That measures what we call performance expectancy. So those of you who are new to research, data analysis, so this PE1, PE2, PE3 are the various questions you use to assess what we call the performance, okay, performance expectancy. The various questions you use to assess the latent variable is what we call the indicators or the observed variables or the measured variables, okay, good. So you can code them 1, 2, 3, 4, 5, depending on the scale you are using. So you drag the latent variable, the indicator variables and put on the latent variable. Yeah. Once you are done, so you do that for all the constructs in your model, you do that, and then you should be good to go. You should be able to create the run the analysis. All right. So briefly, that's how to create a model. All right. You go to create project, accounts, you go and import the data as I have done. Then you draw the diagram, the path diagram. After you are done with that, then you run the analysis. So I'm going to discard this and straight ahead go to this. All right. So I'm going to presume that we are all on this page. Okay. Once you are here, what you do is that you run what we call the PLS algorithm or the consistent PLS algorithm. Okay. So you click on calculate. Now, you should note that if you are on the data view, you'll not be able to see the calculate sign or the menu for calculate. So you have to be on the path diagram where you have drawn it, and then you'll be able to see the calculate. Then you click on calculate, and then you run PLS algorithm. So as I said the last time we met, you're going to do what we call, you're going to evaluate the measurement model, and you're going to evaluate the structural model. All right. The measurement model, you're going to look at the outer loadings. You're going to look at the Cronbach alpha. You're going to look at the composites reliability, the AVEs, the funnel and LACAC, and all those things. Okay. So let me run that. So PLS algorithm. Now, from here, the setup, you see centroid, factor, and path. What we are doing is a path analysis. So by default, the path will be activated. So you choose path. Now, if you want to see how the various latent variables, if you want to see how this various latent, indicator variables are going to perform when you run the path model, you can run what we call the factor analysis or the factor. All right. So for those of you who are conversant with SPSS AMOS, what you do is that you run the CFA first, okay, and see how the items are rotated and which components measures what. All right. You can do same in SmartPLS too. All right. For instance, you can click here, the factor, and then you start your calculation. Great. Now, so once the calculation is done, let me close this. We don't need this. Right. Let me close this too. Great. Once the calculation is done, you see the values that are assigned to each of the indicators. So these are the various factor loadings for each of the latent variable constructs, okay? The various indicators, these are the loadings. So straight ahead, you'll be able to see which items will load like a threshold lower than the acceptable threshold, okay? Good. So this is the factor, all right? So if you are interested in seeing the various outer loadings, good. So when you see the outer loadings, you see B. Okay. All right. So sorry for that. I was told the screen is not recording. All right. So if some items are low or lower than the threshold of 0.7, you can delete them and rerun the analysis again. There might be an improvement in the metrics. Okay, so that's the trick about it. So if FC is 0.57, we can go back and check whether all of them are above the threshold. They are above it. So there's nothing you can do about that. I mean, just let it go. Okay. Yeah. So the next thing you're going to look at is the discriminant validity. You come to navigation and then you select discriminant validity. Okay. Now, in discriminant validity, you're going to look for funnel and LACAC criteria. If you were here last week, we looked at what it says. Okay. So this is the table, a table for the internal consistency reliability, how you report it. Right? We have the Cronbach composite reliability and the remark. Yeah. And, yeah. Any questions so far? Any questions? All right. I presume there are no questions. So, okay. So let's go on. So the next thing we are looking at, as I said earlier, we're going to look at what we call the discriminant validity. Said, how did you open PLS algorithm if you don't mind, please? Number 2. I don't understand your question. If you can unmute yourself. Okay, good. So how did I open this? So what SmartPLS does is that anytime you recalculate, it produces a new, how do we call it? A new result for you. So for instance, let me rerun this again. The gentleman or lady who asked the question. Great. So you see, I have recalculated. So it has given me run number 3. All right. So as you keep running, it keeps giving you a different like windows. It opens different one. I hope that answers your question, please. Yeah. So fast forward. We go back to our report and then we look for number 1. We're going to look for what we call the discriminant validity. So now we are done with the construct reliability and validity. We are going to the discriminant validity. Discriminant validity, you're going to assess it using the Lakak, Funnel and Lakak criteria. You're also going to use the cross loadings and you are going to use the Hcmt, heterotrait monotrait ratio. Those are what you use to assess what we call the discriminant validity. Okay. Good. So the Funnel and Lakak criteria, if you remember, we said that the square root of the AVEs have to be greater than their adjacent relationship with other constructs. And then we looked at how we can do that. We can square the AVE. So let's say square root of AVE over here. All right. So we're going to do a little Excel computation. Then we click here, enter. Then we drag this value down. All right. So that's the formula you use to calculate square root for those of you who don't know. Yeah. So this value over here, or these values, are what we call the square root of the AVE. So to be able to assess the Funnel and Lakak criteria, it says that when you square this AVE, it has to be greater than their interactions with other latent variables or other variables. Now, the same result over here, the same result is what is presented over here. Okay, let me minimize this a little. Good. I hope you can see though. This 0.719 and this 0.719. So the same results I just did the computation for here, over here, sorry. The same results are what is represented in the table. Okay, good. Now, so for Funnel and Lakak criteria, when you take BIBI, it has to be greater than its interaction with other constructs. Okay, so if you take 0.719, it should be greater than what is here, what is over here, what is over here. All right. Now, so it moves in a diagonal form, okay, from top coming down. The next one, okay, let me highlight this. Yeah, let me build it. Good. When you come to 0.836, it has to be greater than what is over here. All right, 0.505 and its adjacent loadings. Okay. So this one, the EE has also met. When you come to FC, it has to also be greater than its adjacent loadings. Okay, its adjacent loadings. All right, so this has also met. When you come to PE is 8.35. Okay, 0.8. It's higher than 0.321, higher than 0.428, higher than 0.437. Okay, you do same for SN, and then you do same for use. Okay, good. So looking at this table, Fornell and Lacan criteria has been met. Okay, when you're using that to assess discriminant validity. Now, the next one you're going to look at is what we call the cross-loadings. Okay, the cross-loadings. Now, the rule for cross-loading is that if you want to know what cross-loadings are, they are all in the first PPT. Okay, so basically, when you take the cross-loadings for each of the indicator variables, it has to be greater than their adjacent interaction with other constructs. Okay, so whilst Fornell and Lacan is looking at the latent variables, cross-loading is looking at the interaction of the indicator variables with other indicators of their respective latent variables. All right, good. So it also follows that diagonal path, So when you take BI has 3 indicators that were used to assess it. All right, so if you take this value here, 0.730, 0.704, 0.723, all of them should be higher than their interactions or their adjacent loadings. Okay, all right, so you see 0.73 is higher than 0.341, 0.34, and blah, blah, blah. Okay, then you come to EE. EE has 4 indicators, right? So EE 0.835 to 0.853. They are all higher than whatever is here and whatever is here. Okay, good. So that is how you assess the cross loadings. So you do same for the other construct. For time's sake, I'll not do for all of them. That's how. So you can just copy this table and then put in your Word. If you go to the PPT, I've presented it nicely. Sorry. Good. So this is the table you use to assess the Cornell and Lacan. You input it, you can square the AV and highlight all of them. The cross-loading, you do same, and then you highlight them in a diagonal form. Okay, great. The next measure we're going to look at is the Hcmt. Okay, the heterotrait monotrait. All right. The rule for assessing the Hcmt is that it has to be different from 1. Okay, the values for Hcmt has to be different from 1. Now, different from 1, some researchers have also suggested that it should be less than 9. So depending on whatever literature you're using to back your value, you go ahead and then report it. So when you see from this diagram, you see that the HTMTs are all in green, meaning that they are met the requirement. So the 0.735 in that order, all of them have met the requirement for assessing HTMT. All right, so great. So the pictorial diagram even gives you an indication. All right, HCMT, all of them are green. So meaning that they are significantly different from 1. Now, so that is for, so still we are assessing or we are evaluating the measurement model. Okay, a quick recap. We have looked at the construct, reliability, and validity, where we looked for the Cronbach alpha, the composite reliability, and then the AVE. Cronbach and composite reliability, the threshold is 0.7 and above. the AVE has to be above 0.5. Okay, good. The discriminant validity, which we are assessing right now, we said you can use the Funnell and Lacarte criteria where the square roots of the AVEs are higher than the adjacent relationship with other loadings. Then when you come to the cross-loading, the indicators have to be higher than the adjacent relationship with other loadings. Then Hcmt, we are saying that it has to be different from 1. That is, it has to be less than 0.9. Okay. Now, the next thing you're going to assess is what we call the outer loadings, the loadings of the indicators. So you click over here. When you come to the final result, you see outer loadings. You click on outer loadings. All right. So outer loadings, the requirement is that it has to be above 0.7. All right. All outer loadings have to be above 0.7. So you see for BI, all of BIs are above 0.7. When you come to EE, they are also above 0.7. FC, same, the same, and this one too. Okay, great. You can straight ahead even see from the path diagram over here. So these are what we call the outer loadings. Okay, great. So how do you report that to? If you're good. So this how you report the HCMT. Okay. So HCMT doesn't include 1. So you input yes or no. Yeah. Cross loading. So let me see. Okay. Good. Great. So the convergence validity, you see the notations, and then you can put your outer loadings values here. All right. Okay. Any question before we move on? Yeah. So the table you see here is a summary of the reflective measurements. Okay. So we have the outer loadings, the AVE, HCMT, composite reliability, and then Cronbach alpha, all of them. This is how you put them into a summary table. Okay. The next thing we're going to assess is what we call the structural model. Okay. The structural model basically helps you to determine the model's capability to predict one or more target constructs. All right. So you're going to assess that using the co-linearity assessment. You're going to look at the path coefficient. You're going to look at the coefficients of determination, that is the R-square values. You're going to look at the F-square values, then the blindfolding, then the effect size Q squared. Okay, good. So to assess the structural model, so in brief, the structural model is basically what you use to test the significance level of the various constructs, or to use to test your hypothesis. Okay, so if you remember, we posited some hypotheses earlier. All right, we posited 6 hypotheses. All right, so we're going to see whether it is true that performance expectancy has, and note the items in red, okay, has a positive impact on behavioral intention. All right, so we're going to go to the PLS, and then we're going to run what we call the bootstrapping. Okay, I have a private message. Okay, good. Any question on the measurement model? Any question on the measurement model? Any question? Any question on the measurement model? No. Okay, good. So we're going to assess the structural model using, okay, good. Using what we call the bootstrapping, okay? So we click on bootstrapping and then we run the bootstrapping, okay? Make sure it's on path. We start the calculations. The basic things you need to know about bootstrapping is here. You can avail yourself to them. You can read them and then get familiar with it. Okay. So you can increase the number of iterations. The number of iterations, you can increase it. And then when the iteration should stop, then you run. Depending on the quantum of samples you're using, it takes quite a number of time. Good. So now we have what we call our bootstrapping report. You can export it to Excel as we did for the Pls algorithm. You can export. It's going to take some time to, let me see. Okay. All right. I think it's going to take that time. Okay. So whilst it's loading, we're going to see the various rules or the various thresholds that we need to look for. All right. Good. So the co-linearity assessment, we have to look for values that are less than 5. Okay, values that are less than 5. Any message? Okay, good. Okay, yeah. So my report is done. Okay, so when you come to the bootstrapping report, you come on the final result and then select path coefficient. Okay, when you click on it, you now see the path coefficient. Okay, good. Now let's backtrack a bit. Let's go back to the Pls algorithm. From the Pls algorithm, we can find the co-linearity statistics, okay, or the VIF. Now, so these are the values for the VIF. Now, the rule for assessing the VIF is that it has to be less than it has to be less than 5 or 3, depending on whose criteria you're using. Okay, so according to here and Co, they said it has to be less than 5. If it's greater than 5, then you have potential co-linearity. Okay, so co-linearity assessment, basically you are just looking at how highly correlated the two indicators are. Okay, how they are related. Because our model is a fully reflective model, we're going to use the inner VIF. Okay, so we assess the inner VIF. So this is the outer VIF. All right, all of them are less than 5. This is the inner VIF. Okay, now, from the inner VIF, we can see that all of them are either less than 3 or 5. So it meets both of these criteria. Okay, it meets both of this. So the inner VIF, you can put it into this table. All right. So that's to do with, so that's all the things we'll be looking for in PLS. report. Let's go to the bootstrapping report. The bootstrapping report, we're going to go to the path coefficient. Okay. Now, when you come to the path coefficient, you look for this value. So the path coefficient, or this particular table, is what you're going to use to assess your path coefficient, used to assess your T statistics and your P values. All right. These are what you use to assess whether or not there's a statistical significance. Okay, good. Now, the rule for path coefficient is that it has to be greater than 0. All right. So the closer the value is to 0, the weaker the relationship. Okay. The further it is from 0, the better or the stronger the relationship. Okay. You can find that from here. So you see that all these values are greater than 0. Okay. So it has met the requirement for the path coefficient. Now, the path coefficient also gives you an idea how your hypothesis is performing. For instance, we said performance expectancy has a positive relationship. So that positive relationship, you'll be able to determine that from here, the path coefficient. So you see that all the path coefficients are positive. All right. So now our heart can start settling in its socket. We don't have any negative relationship. Okay, so this number 1, we are good to go. Now, so the next thing you're going to assess in this table is the T statistics. Okay, let me quickly go to the T statistics. Let me show you. Okay, yeah. So you can also see the pictorial view of the path. Okay, you can see that from the report. You can see the pictorial view of the path, the various paths from the algorithm. Okay, good. So you can see the pictorial view. Good. So the rule for assessing T statistics is that it has to be above 1.96. Okay, it has to be above 1.96 or 1.65. Yeah, that's the rule. Good. So let me see here. So the T statistics has to be above 1.65 at significant level of 10% and then 1.96 at significant level of 5%. All right. So we look in this table and then we assess whether it meets the requirements of the criteria. All right. So you see from all of this that is above 1.96 or 1.65. Right. So T statistics has met. Then we look for now the statistical significance of the hypothesis we posited. Okay. Now, so you see the p-values, you know the common values for p-values, 0.001 or 0.05. Okay. So you see all of them here are 0, 0. They are less than 0.001. Okay. So they are statistically significant. Yeah. So this basically, the meaning of this table basically means that all our hypotheses have been supported. All right. Let me quickly go to. Okay, good. So PE has a positive impact on VI. Let's go see that. PE to BI, it has a path coefficient of 0.214. The T statistics is significant and then the p-value is significant. So we accept this hypothesis, okay? We do same for the other ones. EE has positive impact on BI. So for instance, if you were to say EE has a negative impact on BI, then you'll be expecting that EE to BI, the path will be negative. Okay, the path will be negative, and T statistics will be positive, it will be significant, and then p-value will be significant. Good. So for instance, if the hypothesis we posited was that EE has a negative impact on BI, and then we had this value, what we would have done is now to reject the hypothesis, okay, or states basically that it was not supported. Okay. So let me quickly go here. Let me show you the table for. Okay, so this T statistics result. The p values 0.05, yeah, 0.05. Okay, and then the path. We spoke about the path already. Yeah. So that should suffice for testing your hypothesis. Okay, good. Now we're going to look at what we call the predictive relevance, okay, of the in-samples. We're going to look at the predictive relevance. So the predictive relevance, number one, you're going to look for the R-square value. All right, the R-square value, you can get it from the PLS report. So from here, quality criteria. Okay, you see R-square, you click on it. Yeah, so R-square value ranges from 0 and 1. Okay, with the closer they are to 1, the better the prediction. Okay, or the predictive relevance. Right, so you see 0.35. That's quite reasonable. 0.25. So that's how you can get the R-square value. You get it from the Pls Algorithm report. Any question regarding the structural model? Any question, please? Yeah. So you put your R-square value here. Okay. So the next thing we are going to look at is the effect size, the F-square value. Okay. So the effect size basically help you to determine the effect of each of the independent variables on the dependent variable. Okay, what effect has each of the independent variables on the dependent variables? So you can also get that report from the F squared. You can get it from the PLS algorithm report. When you come to F squared, you click on it, and then you scroll down. Okay, good. So what is the requirement for assessing the F square? Okay, so values of 0.02, 0.0, 0.15, 0.35 indicates a small, medium, and large effect of exogenous latent variable. Okay, good. So you check from this table what the values are. This is 0.163. So we go back and check 0.163. That is a medium effect. Okay, that's a medium effect. So effort expectancy has a medium effect on behavioral intention. Then we come to 0.054. That is a small effect because from here it's less than I think it's around 0.02, 0.05. So it has a small effect. Good. So effect size values which are less than 0.02 means that there's no effect. Okay. Great. So 0.059, 0.0, yeah. So all of them. So it ranges from medium to small effects. All right. Good. So you can get that from here. This is the table for the F square. The F square. All right. So the next indicator we are going to look at for assessing the predictive relevance is the Q square. Okay. So the Q square basically is to evaluate the magnitude of the R square that we have examined earlier on the Q squared. Okay, Q square is an indicator of the model's predictive power. Now, please note, this predictive power is not for the entire model. It's only for the in-sample. Okay, so if you want to assess the predictive power of the out-sample, you use what we call the Pls Predict. Mind you, the R square too. So some researchers state that the R square, or mistakenly reports that the R square measures the overall performance of the model. That is not entirely the case. The R square is only measuring the predictive relevance or performance of the in-sample. If you want to look at the total sample, the out-of-sample performance or the predictive power, you use what we call the Pls Predict, not the R square or the Q square. So please take note. Yeah. So the Q squared, basically, you obtain that when you perform what we call the blindfolding. So we come back to our PLS software. We click on the path model. We come to calculate and choose blindfolding. All right. Now, the omission distance, the default is 7. Then you start your calculation. All right. Once that calculation is done, good. So once the calculation is done, we can export it to Excel. This one, because the items we are going to look for in this table are not matched, we can just look for it from here. Okay, good. So you see BI, R squared, Q squared for BI. Okay, good. So you see BI has a Q squared of 0.167, and then use has a Q squared of 0.17. So this is the good thing about SmartPLS. Every report, whatever you need, you just need to know what you want. From the report, you can get it straight. You don't need to go and do any computation apart from the Q squared, the small Q squared. Okay, good. Now, so Q squared values greater than 0 suggests that the model has predictive relevance for a certain endogenous construct. However, values less than 0 shows a lack of predictive relevance. Okay, so we'll see whether the Q squared for the blindfolding is different from 0. And from here, you can see that they are all different from 0. They are greater than 0. Hence, this model has predictive relevance for those endogenous constructs. Okay, good. So you can put this into a beautiful table like this way, here, like here. Okay, so you put this value, put the SSO, you put the Q, you can put, so you can just copy all this table and then put into this beautiful one here. Okay, right. The next thing we're going to look at is the Q squared. the lower Q-square value, okay? So the lower Q-square value is a relative measure of the predictive relevance used to assess an exogenous construct's contribution to the endogenous construct's latent variable. So basically what it means is that, where's my screen? Good. So what it means is that if you see from this diagram, this use is our dependent variable and behavioral intention is our independent variable. I mean, in this particular structure. Okay, good. So now we're going to see the effects, okay, the effects this BI has on the Q squared of this construct, okay, the effects of this on this, all right, effects of behavioral intention on the predictive relevance on the Q, where is it? Good. The effect of BI on this Q squared value. That is what you compute using the effect size, small q. So there are two effect size. One is for determining the predictive relevance of an exogenous construct on the Q squared, capital Q squared value of an endogenous construct, okay? And then the other one is the normal F squared value. So to calculate for the small squared value, small Q squared value, you use this computation. So you take the Q, capital Q squared. So if I say Q squared, I mean capital Q, okay? You take the capital Q squared included minus Q squared excluded all over 1 minus Q squared included. All right, good. So you're going to take from here. So if your mathematics is not very good, this is where you find problems. But I have a tiny Excel program that can do the computation for you. You just need to pick the values and then put into it. It gives you the result for the Q square. I will share it with you when we are done. All right. So you take this value minus this value all over 1 minus this value. Okay. That the result you get is the effect size. Okay. The effect size. So excellent. Good. So that is how you assess both the measurement model and the structural model. Any question before we go on? Any question? Any question? Any question? Any question?
Yes, Laoshi, I have a question.
Yes, yes.
Laoshi, I have a question related to the sample size. Is there any specific condition for a sample size that we use for the smart PSL?
So
how do we select the sample size for all these calculations and the data we collect from the people?
Okay, good. So if you look in the PPT, we have a table that guides you what sample size you should use. So your sample size selection is dependent on the number of latent variables you're going to have in your model. You are going to look at your anticipated R-square values, okay? That determines what sample you should use, okay? So if you have the PPT, you get the table that should guide you what particular number you should select. But basically, a sample size of 200 and above should be sufficient to do any basic PLS analysis. Okay. All right. Okay, good. So the next thing we're going to look at is moderation and then mediations. Okay. Yeah. So if not for the recap, we would have started from here. All right. So mediation basically is present, or it occurs when a third latent variable intervenes between the relationship in two other latent or related variables. So for instance, the relationship of y1 to y3. Okay, good. Y1 to y3 is mediated by y2. All right, that's mediation. Okay, so a change in the exogenous construct causes a change in the mediator variable, which in turn results in a change in the endogenous variable. Okay, good. So when there's a change over here in y1, it causes a change in y2, which causes another change in the value of the dependent variable. Okay, good. So we get that from here. Now, so this diagram, for instance, let me reposition this. Okay, good. So I'm just going to connect. So to do a moderation, this is how a typical moderation looks like. Okay, this is how a typical moderation looks like. It looks like a beautiful small triangle. All right, so this y1, y2, this y3. Okay, so any change, we want to see whether any change in FC causes a change in BI, which in turn causes a change in the use. Okay, great. So what do? You go and calculate. All right, you go to bootstrapping and then you calculate. So if you have to okay, good. So if we were to draw this diagram, this connection earlier, from the bootstrapping algorithm that we had or analysis we had earlier, we would have just checked whether there's a mediation or not. Okay, good. So let's go to our bootstrapping. Now, from the bootstrapping, you can get the total indirect effects and then specific indirect effects. Okay, the total effects and all those things. Good. Now, in determining mediation, you use what we call direct effects and indirect effects. Okay. Now, a direct effect is the relationship between two constructs with a single arrow. So between y1 and y2 is a direct effect. Between y2 and y3 is a direct effect. Okay. Good. While the indirect effect is a sequence of two or more indirect direct effects, which is represented by multiple arrows. So the direct effects, as I said earlier, P3 is between y1 and y3. The indirect effect is y1 on. Okay, from here. Okay, good. So the rules for mediation. Okay, so there are several types of mediation. All right, you can have complementary mediation, you can have competitive mediation, and then you can have no mediations. Okay, so from the flow charts, you see complementary or partial mediation. Yeah, so there are three big blocks. That could be partial mediation, full mediation, or no mediation. Okay, good. And then they are both, the three of them are broken down into pieces, into sections. All right, so complementary partial mediation, competitive partial mediation, indirect only full mediation, direct only no effect, and all those things. Okay, good. All right, so let's go to, yeah, so this is basically an explanation of mediation. Okay, good. So the rule for mediation is that, let me show you something first. So when you come to the path coefficients, all the values you get in path coefficients are what we call the direct effects. All right, the direct effects are all here in the path coefficient. Okay, good. So we have FC to BI, which is a direct effect, and then we have FC to use, which is also another direct effect. Okay, good. Now, so these are the direct effects. So now we see what so bootstrapping, as I said earlier, is used to test for statistical significance. Okay, good. So you see that the direct effects BI, FC to BI is significant. FC to use is also significant. Now let's go and look for the indirect effect. Okay, now the indirect effect is between FC to use. Okay, the indirect effect is between FC to use. Okay, good. So basically, you can also get the whole mediation from specific indirect effects. You can get the whole mediation. So we are looking for the mediation between FC, BI, and then use. All right, you can just get it from here, straightforward. Okay, FC to BI to use as a positive effect. Okay, now, how do you assess mediation? Okay, the rule for assessing mediation is that if the indirect effect is not significant, but the direct effect is significant, then there's no mediation. So if the indirect effect from here, if the indirect effect is not significant and the direct effect is significant, then there's no mediation. Okay, that is number one rule. Number two, if the indirect effect is significant, but the direct effect is not significant, then we have what we call a total mediation. Okay, so if the indirect effect, if this is significant, okay, but the direct effect is not, then we have what we call a full or total mediation. Okay, now the last one, if both indirect effects and direct effects are significant, then we have what we call a partial mediation. All right, so if you take the total indirect effect from FC to use is significant, and then the direct effect FC to BI is significant, FC to use is significant. So in this model, we have what we call a partial mediation. Okay, we have what we call a partial mediation. So you can either have a no mediation where the indirect effect is insignificant. So once the indirect effect is insignificant, whether or not the direct effect is significant, there's no mediation. All right. Now, if the indirect is significant, but the direct effect is not significant, then you have what we call a total mediation. If both the direct and indirect effects are significant, then you have what we call a partial mediation. Okay, good. So in this diagram, what we have is what we call a partial mediation. So there's a mediating. So we can go back to our hypothesis. Okay, good. All right. So I think we didn't put that hypothesis here. So there could be a hypothesis that FC mediates the relationship between BI and use. And then we would have just said that it's supported based on those values. Okay, great. The next thing we're going to look at is what we call the moderation. Okay, so we have looked at assessing the measurement model, the structural model. We have looked at mediation. We are now looking at moderation. So moderation happens when the relationship between two constructs is not constant, but depends on the values of a third variable, which is referred to as a moderator variable. So for instance, if the relationship between behavioral intention and actual use is not constant, but has technology anxiety playing a role on whether or not this relationship is significant or not, then we have what we call a mediation. Okay, sorry, a moderation. All right, the moderator variable changes the strength or even the direction of the relationship between the two constructs. Yeah, so even the path could even change. All right, now how do we have or introduce what we call moderation? All right, now to introduce moderation, we insert a new latent variable. So you click on latent variable, you drop it here, everything changes for you. Get the connector and connect it over here. Okay, good. So let's say we say that technology anxiety. I'm gonna type a bit technology anxiety. Technology anxiety moderates the relationship between BI and use. Okay, that is the hypothesis we are positing. And have that new variable. So we're gonna imagine that PI, P2, P3, P4 are values for technology anxiety. Okay, now what we do is that we stand on the dependent variable and then you right click. Sorry, you right click and then you add moderating effect. Okay, so the dependent variable is use. Moderator, so you choose from here. Moderator variable is what? Okay. Okay, good, good. Yeah. So we stand here, choose the moderating effect. Moderator variable is technology anxiety. The independent variable is just a moment. Let me see. It seems I've drawn this model wrong. Okay. Let me delete this. Yeah. So here. Okay. So right click, moderating effect, use. Okay. Technology anxiety independent is BI. Good. All right. So now we are saying that technology anxiety moderates the relationship between behavioral intention and then use behavior. Okay, good. Now the calculation method, you can choose product indicator or two-stage indicator. What basically it means is that when you take the two-stage indicator, it multiplies, it takes the whole latent variable, put them to, the indicator variables for the various constructs, it put them together and then multiply the other one. But when you take the product indicator, it multiplies each of the indicators. Okay, so we'll see. Basically, let's see how it performs. So this two-stage. Okay, so we click OK, and you see it introduces a moderating effect over here. Now, let's right click and then let's show indicator. Good. So you see from here, if you take a two-stage, it takes the latent variable and then multiplies it with the other latent variable. Okay, that is what it does. Now, let's delete this and then see what the product indicator does. BI. Good. Product indicator. Good. We come here. Let's show. Yeah. Let's show. So you see, if you take the product indicator, it takes each of the indicators and then multiply them. Okay? Takes each of the indicators and then multiply them with the other indicators. Whilst when you take the product, it takes only the latent variables and then multiplies. Okay? Good. Now, I would suggest that you use the product indicator because it gives you a more reliable result. The error terms are more minimal and those things. So I suggest that you always choose the product indicator when you are calculating for your moderation. All right, good. So now we have introduced our moderating effect. Okay, good. So now let's go and then run our analysis. So for moderator, when you introduce the moderator, what you do is that you assess the measurement model and assess the structural model too. Okay, the measurement model you can assess using the Pls algorithm, and then the structural model you can use the bootstrapping. All right, because we have done all these things, I'll just go ahead. We'll not go and then talk about the loadings and all those things. I'll go ahead and then run the bootstrapping, okay, to test whether there's statistical significance. All right, so I come to bootstrapping, I calculate the bootstrapping. Any questions so far? Any question on the mediation? Any question? Any question on the mediation? No question. Good. All right. So if there's no question, okay, great. Okay, good. So now this is the bootstrapping. Okay, this is the bootstrapping. So we're looking for the moderator variable. So you see moderator one to use. Okay. You see from this value, okay, you see from this value, the p-value is above the threshold. Okay, so once it's above, basically there's no moderation. Okay, once it's above, there's no moderation. I mean, so the moderating effect is not statistically significant. So there's no moderation. So basically, technology anxiety does not moderate the relationship between behavioral intention and actual use behavior. Basically, that is it. Okay, good. Yeah. If you run the algorithm report, you can even see. So if there was a moderation, would have gone to plot the diagram. Okay, would have gone to plot the diagram. But there's no moderation, so you don't waste time plotting the diagram. Okay, good. So simply that's how you calculate, that's how you perform moderation. Okay, there could be instances where you could have chain of moderations. Okay, yeah, that is quite advanced. I think another time we'll look at that. Okay, so that is how to perform mediation and moderation. Right now, the final thing we'll look at before we go is the Pls Predict. Okay, so earlier on, if you remember, I said that I said that the R square the coefficients of determination, that is the R square, and then the Q square are just predictive relevance for the in sample. So if you want to see the out sample, you use what we call the Pls Predict. Okay, good. What Pls Predicts does is that, so it's a procedure used to assess the outs of sample prediction. It involves the estimation of model. Okay, good. So it involves estimating the model on an analysis or a training sample. So basically what Pls Predicts does is that it takes the total sample size you have and it breaks it into what we call folds. So it does what those of you who are advanced in statistics or computer science, it does what we call a cross validation. So a cross validation basically is that it's going to break the sample size you have into folds. So say 10 folds, it's going to break it into 10 folds and use a portion to run or to estimate the model. After it is done, it will use the other holdout sample to test the model. Okay, good. So basically all we are doing, for instance, in social science, is that we want to be able to build a model for someone to put whatever value into and run analysis and be able to take a decision. All right. So now, if you have designed the model, how sure are we that when someone inputs a data into it, it can be able to perform an analysis on it to the point where the person can be able to get similar results as the original model did? All right. So basically, that is what Pls Predicts does. Okay, good. So there's what we call a holdout sample. Pls Predicts executes a k-fold cross-validation. A fold is a subgroup of the total sample, and k is the number of subgroups. Okay, great. So, yeah. Okay, good. So, the literature for Pls Predict is here. All right, you can just go to your path model and then you go to calculate and you see Pls Predict. Okay, and then you select it. Now, so you see the number of folds. The number of folds basically means that how do you want the total sample size to be broken? Like into how many sections, into how many subgroups do you want the data, the complete data set to be broken? Okay, great. So even from here, they said in k-fold cross-validation, the algorithm splits the full data set into k equal size subsets of data. The algorithm then predicts each fold, a holdout sample, with the remaining k minus 1. All right, that's the holdout. K minus 1 is the holdout, which is in combination becomes the training sample. For example, when k equals 10, that's a 10-fold cross-validation. A data set of 200 observations will be split into 10 subsets. Okay. Somebody has just sent me a message. Okay, good. I will. So, yeah, before that, good. So a subset, a data set of 200 observations will be split into 10 subsets with 20 observation per subset. Okay, so the algorithm then predicts 10 times each fold with the 9 remaining subsets. All right, so basically that. So the repetition, the number of repetitions or the number of iteration, okay, the number of iteration, because it's a model you are building, it wants to be able to run the iterations to the number of times or to the maximum number of times so that it reduces the error terms. Okay, good. So the default value is 10. All right, and then it's recommended that you use the 10. You leave it, so you leave everything intact there. Then you run the Pls Predict. Okay, good. So there's a singularity metrics problem, so we can run the PLS predict. Oh, sorry, I didn't notice this. Let me see it. Okay, so we have an issue of singularity. Let me see. Let me delete this and see. Okay, good. Okay. Let me okay. Great. So the data is problematic. So I'll use a different data to illustrate the PLS predict. Okay. Yeah. Because the data we are using is a hypothetical data, there's issues of singularity. So let's hope this one does it. Excellent. All right. So basically, this the PLS predicts table. This is the results that it presents. Okay. Now, so the first thing you look for is the Q squared, capital Q squared predict. Okay. Now, so from here. Just a moment. Good. So Q squared predicts values should be higher than 0 to indicate that the model outperforms the most naive benchmark. Okay, good. So when this table opens, when it opens, you check from the Q squared predicts values and see whether they are different from 0. Okay, in other words, are they higher than 0? Okay, and from here, they are all higher than 0. So it means that the PLS predicts, okay, the model outperformed the most naive benchmark. That is the least linear regression model. Okay, good. So after you have assessed this, what you do is that you compare the error terms. Okay, good. You do a comparison of the error terms. So the error terms, you can either use the root mean squared error, the RSM, or the MAE, or the MAP. You can use any of them. All right. So now what you do is that you compare, for instance, if you are going to use the RMSE, you're going to compare the values, okay, for our target construct. So if you take this diagram, the target construct is, this might sound new because it's a different data. This customer relations, yes. So this CUSL, this our target construct, okay? So this three, this are target constructs, all right? So we first check their Q squared predict values. They are different from 0. Then we check from here. So in the PLS, under the PLS tab, okay, this is the PLS prediction tab, all right? So we check the error terms, okay, and see whether there's a difference between the PLS predicts results and then the least square or the benchmark. So it sets a benchmark of error and that's a comparison. Okay, so the LM tab is the linear regression model tab. Okay, so you compare these values over here under the LM tab with their corresponding values over here under the PLS tab. Okay, good. Now, how do you do the comparison? Okay, so if the PLS Let me bold in this a bit. So if the PLS SEM analysis compared to the naive, okay, yields a higher prediction error in terms of RSME, it indicates for all the indicators, it indicates that the model lacks predictive power. Okay, so if the values under the PLS predict menu, so this 1.3, 1.524, 1.532, if they are higher than this ones, then there's a lack of predictive relevance. Okay, so this 1.30, this 1.315. So this is rather higher. The linear regression model is higher. This 1.544, this 1.524. Okay, good. So it looks as if almost all the loadings or the values under the RMSE under the linear regression model are higher than the PLS predicts. Okay, good. So let's see. So this one has not met. So there's a potential. So it means that we rule out this one. Okay. Now let's see the next one. If majority of the dependent constructs indicators in the PLS analysis produces higher prediction error compared to the naive LM benchmark, it indicates that there's low predictive power. Okay, good. So if majority of the values here are higher than this, then meaning that there's low predictive power. If the minority of the same number of indicators in the PLS SEM, that's this, if this values over here are the same as the values over here, then we have a medium predictive power. Okay, now if none of the indicators in the PLS SEM analysis has higher RSM values compared to the naive benchmark, then the model has a high predictive power. Okay, good. So we see that all the values here in the PLS predicts menu for the target constructs, they are all lower than their correspondence in the LM, the naive benchmark table. Okay, so since they are lower, we have what we call a higher predictive power. Okay, so we have a higher predictive power. All right, so for PLS predicts, you first of all check for the PLS, the Q squared predict, then you compare the error terms between the PLS and then the linear regression model, right? You compare and then you use the benchmark to assess them. Okay, so that basically ends our basic introduction to statistical analysis or PLS SEM analysis using SmartPLS. If you can look for other literature. If you take the first one, this paper, it gives you the APA writing format for how to like report your values. Yeah, same way the PPT and the PPT2 have redacted most of the things and puts there. Okay, so if you're looking for literature to support how you report it, it's here. You can further read from these guys. Yeah, when to use and how to report the results of PLM set and all those other ones. You can also check the PLS SmartPLS website where you can be able to get some additional resources and then sample like projects that you can run and try your hands on and all those things. Okay, good. Thank you very much. Good luck and see you next time.